Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
Hello, everybody. Hello and welcome
to another episode of Ask Us Anything About Electrochemistry.
It's like we're finishing each other's
sentences.
Oh, you're supposed to say sandwiches.
Oh, that was, I know.
What's that from? Is that from a movie, right?
There was a movie.
It's like we finish each other's sandwiches.
This is when Dane Cook was a very,
was it?
Yeah, when he was a popular comedian. He was in a movie, and
I feel like it was from an
so.
animated movie. Like,
oh, an animated movie?
like one of the, like was it Inside Out? There was a new one of those recently.
I heard that was good.
It's like, we're so attached, we finish each other's sandwiches. I feel like that was a thing. I can't remember where it's from. Anyway, I'm getting totally off the rails already here, but that was it's gonna bother me. I got to figure out where that's from after the stream at some point.
Oh,
I
yeah.
need to like find it. It's pretty funny.
Oh no, that's all good.
Anyway, thank you for that, humoring me.
Yes.
Welcome everybody.
Yes. And now that you've listened to all the boilerplate stuff, we can go straight into questions. It looks like Barry, good to see you, Barry, has a question. Barry's asking, do I need to add both AgNO3 and TBAPF6 to a non-aqueous reference electrode?
Maybe.
This is a good question. Generally speaking, so the silver nitrate is the, that's the thing that's kind of, quote, governing the potential of your reference electrode. So you're adding a concentration of silver nitrate, ideally the silver plus, like silver plus, or silver oxide silver plus redox couple is the thing that's governing the potential.
I feel like the TBAPF6 might be superfluous if the AgNO3 concentration is high enough.
Yeah.
Right. The only thing that gives me pause about what I just said would be from the perspective of, let's say your main electrolyte solution is, 0.5 molar TBAPF6 and, ferrocene, whatever you're using. It doesn't matter. Having some TBAPF6 already in your reference electrode will, in theory, minimize crossover between the bulk solution and the reference electrode, because it will be, whatever you want to say, relatively isotonic between both. So, otherwise, just by diffusion over time, you'll end up with some TBAPF6 like leaking into the reference electrode compartment anyway. So you could probably add some, and then that will make it so there's almost no diffusion either way. That's my only thought, I guess. I don't know that it's going to matter for the reference electrode performance, because as you said, Alex, it's governed by the Nernst equation, which is governed by the activity primarily of the Ag+.
Yeah. You can, there is a little tiny thing that's not talked about often, which are called liquid-liquid junction potentials. Which is when you have kind of two different solutions, and if they're charged solutions, which we're dealing with, you can form what's known as a junction potential. But junction potentials usually only cause a few millivolts in like a potential drop or a potential difference. So I don't think it's going to be a really big issue in this case. But generally speaking, I think it's a good idea to add a little bit of TBAPF6 because you will have diffusion of those back and forth.
I agree. And I think the main thing is it probably won't hurt you. So you might as well, in other words, it's probably not going to negatively impact the reference electrode performance in any meaningful way. And for all the reasons that we just said, it might
Yeah.
it might improve your experiment. So yeah, it's probably a good idea to add some. Given the solubility constraints, because obviously non-aqueous solvents do have a typically lower total like ability to dissolve. In water, aqueous you can have like 5 billion molar of a million things. It's easier to dissolve more stuff in water typically. So just throwing it out there, if it's sort of like, well, it won't dissolve because I already have 9 molar of this and 10 molar of that, whatever. So just keep that in mind. But if you can, I think it's probably a good idea. Yeah.
All right. Cool.
All right. So it looks like Wojtek is here.
Okay.
And saying you had a question. I do have your question. It's actually, we have a couple of questions, actually like 2 or 3
We can get
ready to
some
go.
later.
So we'll get to yours, Wojtek, because since you're here,
Yeah,
thanks
since you're
for
here.
joining. As ask and you shall receive. I actually have it teed up already. Let me pull it up here somewhere. Nope, not that one. Why? Hang on. I have the question. And I will find it for you. There it is. It just wasn't wanting to show up. So I just have it kind of copied. This was a comment that you made on a YouTube channel. So I know hopefully I'll try to zoom in a little. You can see. So Wojtek had said, hey, I'm wondering.
Yeah, we can make this big if we want. We can.
Yeah, I was just going to. There we can see all the question. So I've cut off your face a little bit there. Apologies. But anyway, I'm wondering, how does measurement of EIS and then determination of the diffusion coefficient look like experimentally? So basically, I prepare a lithium coin cell. Then what? Does it have to be charged or discharged first before doing any EIS measurements? Or I just start doing EIS immediately after preparing the lithium coin cell and waiting a bit? So that's sort of the first part. And then second is to determine the value of the diffusion coefficient. How difficult is it to do these fittings? Does it happen kind of automatically in the software after proposing a scheme for the cell? And it looks like I'm just checking in the question 2. Basically, let me see if this is the same one as before. I'm just going to double check. I have organic electrode material as a lithium salt. I'd like to determine the lithium diffusion in that material. How do I do that? Possible to do it without additives on pristine material. Right. Okay. Let me try to tackle this like a little bit at a time here. So the first thing that you had said was like, I make my coin cell. Can I just start testing immediately? Like, what do I do? Right. Generally, as a rule of thumb, make your coin cell and then run like 2 or 3 charge discharge cycles, then do testing that you'll run diagnostically, like EIS or actual charge discharge. Like you'll run a slow scan, like put together your battery, and then you'll either charge or discharge it to whatever the appropriate limit is, upper or lower, and go up and down like 2 times maybe, fully, and then consider it fresh and start, and then you can do whatever. There's a couple of reasons for that. The first is that you have to get the SEI to form most of the time. The anode functions primarily with what's called a solid electrolyte interface. Lithium half cell, just to clarify. Yeah, so you have a half cell. So you will need to do that. Whether or not you're studying the cathode or the anode, you will still need to form the SEI. And it is a dissolution partially of the electrolyte on the anode surface. It's a film of decomposed electrolyte products that prevents future decomposition, partly because batteries involve such high potentials that they can lend themselves to ripping the electrolyte apart, which is one of the mechanisms of thermal runaway and failure. And so the SEI is a naturally protective layer, and it has to form. And typically what it does is form during the first discharge of your battery once it's been put together, leading to a larger than expected capacity. You'll observe a way larger capacity than you should get. And it's just because there's a bunch of current that is going to forming the SEI. And then in subsequent, so I'll draw something rather than miming in the air like a clown here. I will do that. So for instance, with your half cell, here we go, drawing stuff. So this would be capacity. So this would be like amp hours, and this would be voltage. And so this is your upper and your lower limit. And so if your first charge or discharge, I'm honestly forgetting. I feel like it's the charging would form it most probably, because that's the charging is a reduction at the anode, and that's probably what's going to form your SI. So let's just pretend it's the charging. But you get the idea either way. So your first charging might look something like this. And then your first discharge will be like that. And it's like, wow, that's terrible. But it's like all of this, I should do it in blue because I did it blue. All of this right here, like most of this is SEI formation. Okay. And then subsequent charge discharges, you might do one more for good measure, however, but you'll then like the next ones will be, like whatever, like reasonable values. And then it will go from there. So it's like everything over here is like greater capacity than you would expect to have. And it's like, it's just the first couple of tests. You just ignore it. It's setting up the battery. Because when I said in my response on YouTube, one of the things that I had said to you was, it depends on whether the cathode is lithiated or not. And so what I mean by that, I know you said you have a half cell, but for those who are doing full cells, for example, the anode typically consists of carbon. Cathode is usually a transition metal oxide. So let's just use the simplest example, one of the first ones, lithium cobalt oxide. Okay. You can see here, if you have these two materials, the only place lithium exists is in the cathode. Initially, it's lithiated. So if you don't have lithium cobalt oxide, and you just have cobalt oxide and carbon, well, there's no lithium. You don't really have a battery. So usually the cathodes are pre-lithiated. Okay. That means it's fully discharged. Lithiating the cathode is discharging it. And so to make the SEI, the lithium ions will go from the cathode to the anode, and part of that current will be this plot here. You'll get that kind of SEI forming. Okay. And so that first, look, the only way you're going to do impedance on that first scan is if you want to study the like initial SEI formation, which you might, fair enough. But if you're trying to study like the fundamental application of the battery and the cathode, the anode performance over time, and not the initial sort of, procedure, then you're going to want to skip those first couple of steps or whatever. Right. So there's that. Okay. So that answers the first part of the question. I think here now you basically, so that was, sorry, I know I had it and I got rid of my little question, which is not helpful. So I'm going to take a look at it again. I know you asked them here, but I want to read the rest of that question as soon as it's being really great. Right. So do I have to do anything, or do I just do and wait a bit? Okay. To determine the value of the diffusion coefficient, how difficult is it? Does the software do it? Yeah. So basically measuring the diffusion coefficient, how easy. It's somewhat related to your second question here. And the second part of your first question, like how it's determined or whatever. I'll go through this with the Warburg. So there are different methods for measuring the diffusion coefficient. There's one called the current pulse relaxation technique, which is not an EIS technique. It's like chronoamperometry or chronopotentiometry. PIT and GITT have ways of measuring the diffusion coefficient, mostly through a relaxation, an open circuit. You can correlate the decay of the potential essentially with diffusion. There's ways to do that, but what you appear to be asking about, and a popular common method, I would say, for doing this is by using impedance. Okay, and specifically Warburg elements. So I'm gonna walk through that a little bit with you and try to answer that question. So this is actually, I'm gonna share my screen so I can do the presentation. Change my mind.
Okay.
Screen. So this will be a bit trippy for a second until I do this. Okay. Make sure it's sharing properly. Okay.
Yep, it's sharing.
So I'll go over this. This is from my my webinar on impedance in the third part where I talk about Warburg elements. I'm going to go through this relatively quickly here. I know might be some other questions. We have a few to get to, but so the Warburg element is the most common. The infinite Warburg element is the most common Warburg element that we use, and it's basically sort of definitional of the impedance of diffusion. Okay. And so we're considering semi-infinite diffusion from an electrode surface. Now with a battery, we don't always get this kind of diffusion, but we're going to just walk with this one first here because it's the simplest, most straightforward example. And so it essentially describes a situation where you have an electrode, you have a species A, for example, in solution, it diffuses to the surface. Once it reaches the surface, it's within the inner Helmholtz plane or whatever you want to say. A goes to B. We have some process here, and then B diffuses away, right? So we have diffusion of both species where, whatever you say, I'll get into this in a second. Which one are we trying to measure? In your case, you're talking about measuring the Li plus, which is usually what we're trying to measure here. And in the battery, it's a little bit different. There might not be a diffusion away, right? Because it's like maybe the lithium ion is diffusing and then it forms my species B is like a solid material. It's like the intercalated thing. So this is a general sort of case you're looking at right now. In the case of a battery, it might not be exactly the same, but the mathematics of the impedance are shown here. The impedance of a Warburg is equal to a constant, and then it's divided by j omega to the 1/2 power. And the diffusion coefficient comes from this. This is straight out of Barden-Faulkner. This is the relationship between the Warburg coefficient that is obtained directly from circuit fitting in the software. I'll show you that in a second to answer that part of your question. How easy is it? Basically, it relates to the diffusion coefficient of both species in general by this equation here, okay? And so there's a fundamental question that has to be answered with this that often is skipped over. A lot of times what we do, and what I used to show in all of my webinars actually, is you just sort of neglect one of these terms, like neglect the B, and then just solve for dA to the 0.5 in the denominator here. Okay, we'll just neglect one of these. But it's actually kind of a little more complicated than that to work out which of the species I'm measuring. And it's sort of, you can think about it as being potential dependent. And so to do that, to look at the dependency between potential concentration and therefore the diffusion coefficients, we have to look at the Nernst equation, which makes Alex happy. Yes. And so this is the Nernst equation here. The potential, it states that the potential is equal to the standard potential E0 minus some constants, RT over NF, times the natural log of the reaction quotient. And so for us, this is just a simple example here. A plus NE goes to B, like we're seeing here. I'm skipping right over the activity. Activities aren't real. Nobody cares. We're going right to concentration, right? So technically it's activity of B over activity of A. I'm just assuming concentration here for those who are aware of that distinction. You can just acknowledge, I'm acknowledging it exists and we're moving right to concentration. So effectively we have this term natural log of CB over CA, and that's the critical thing. Okay, so there's 3 cases I'll go over relatively quickly here. When E is at the standard potential. So kind of if you have one redox species, you might consider this to be the open circuit potential, will probably line up with E0. A lot of people do impedance at OCP. But whether or not that's actually what it is, if you are in theory at the standard potential, look at the Nernst equation here. What does this mean? If E is equal to E0, that means that CA is equal to CB. Because looking at the Nernst equation here, if CB over CA is 1, the natural log of 1 is 0, this term goes away, right? So just mathematically, I'm just working out here. For E to be equal to E0, logically, it means from the Nernst equation that the concentrations of A and B are equal. Now go back to this equation. Why does that matter? Well, it relates to the Warburg equation and the diffusion coefficient. So if CA and CB are equal, well, what it kind of means is you sort of end up with this situation. I know this is a bit weird to think about. It's like, well, DA and DB are different, but what is sort of built in here is that we kind of have this average diffusion coefficient of the A and the B species effectively, because the concentrations are equal. So they sort of, you can assume this sort of has the same denominator, and we get a sort of aggregate of the diffusion coefficients. I know this isn't like perfect mathematics here, but I think this is somewhat of a generalization of how this equation is simplified, if you will. Now, there's 2 other cases that make it a little bit easier in a sense. So one is if we push this potential less than the standard potential. So this is pushing towards the reduction pathway. This is sort of a definitional electrochemistry phenomenon. When you have the potential less than the thermodynamic E0, you're pushing it in the reduction direction. And so this is pushing it to more B, right? So what this means is, by that definition, we're going to have more B than A. We're using it up. We're going in the reduction direction. And so there's more B. So you can look at this equation again. What we have is that CB is greater than CA. So CB divided by CA is greater than 1. The natural log of greater than 1 is a positive number. So RT over NF, natural log of a positive, this is a positive number, E0 minus a positive number. So E is less than E0, right? Mathematically, by the Nernst equation, we're taking a positive number away from E0. So E is less than E0. So in other words, going backwards, if E is less than E0, the concentration of B is greater than A. What does that mean here? Well, it's sort of counterintuitive. If the concentration of B is greater than A, we can neglect it because it's 1 over, right? CB is in the denominator. So the bigger the denominator is, the more close to 0. 1 over a large number is 0. So this goes away, and we can simplify it to basically being here. So one way to look at this is that if we are reducing for our standard process at a reducing potential, then we are measuring the diffusion coefficient of A. So by that logic, if we are measuring Li plus electron intercalates or something like that, we want to be doing that reduction reaction, which in the case of an anode is charging. It's charging up the battery, charging up the anode. Then we would be inferring, again, to your point, like a pristine material, the lithium ion diffusion coefficient, if we're reducing the lithium to metallic lithium or to intercalated lithium or whatever it is, we are in theory at enough of an overpotential there, neglecting the diffusion of any other species, and we're studying mainly, in theory, the Li plus diffusion coefficient. And then by extension, I'm just going to go through this very, very rapidly, but you can imagine the exact opposite situation. If E is at an oxidative potential, you're pushing it the other way. This number is less than 1, which means the natural log is a negative number. This is negative minus a negative is positive. This is greater. CA is greater. We neglect this term. We're measuring B, right? Obviously, the converse is true. I think the other case is the one that mattered more to your question. And so finally, and then I promise I'll shut up for at least a long time.
That's good.
How does it fit, right? So here's one example of a battery that shows this kind of infinite Warburg sort of tail at the end here. Okay, so I'll try to fit this somewhat quickly and show you. It depends on the battery. I'll just show you 2 examples. Okay, so here's a type of circuit we might use. I'm going to use a CPE instead of a Warburg, but you get the idea. It's basically the same thing. I'm also going to neglect the inductive tail because it's irrelevant and mostly meaningless. There's an Easter egg for you. It's mostly meaningless.
I think I might be the only person who really appreciates this.
I did it for you.
I know.
I didn't do it for anybody else. All right. So one of the things about batteries that's annoying, frankly, is that they have extremely high capacitance and extremely low resistance. So it can be very tricky to fit sometimes. Okay. So I'm going to go through this somewhat fast here. I need to increase the limits of my CPEs so that it will be able to find values at all. I'm going to lock actually this one at 0.5 because that is, 0.5, that's the Warburg element. And then I need to reduce the limit of these because it's actually like 6 ohms, or it's really small. The resistances, they get very, very small. And in fact, milliohms, so we're at like 50 something milliohms. So that's about actually pretty good, 50 whatever milliohms. Whoops, I had it right. Go back. I'm just going to lock that one in place so it's not terrible. And this one looks like it's between 60 and 70, so it's probably like, it's actually right about 10. We'll just lock that in place. Let's see if we get something to start with. Okay. Have I maximized this? I've maximized this. Oh yeah, that's in the wrong unit. All right. So there's that. There's that. All right. I'm somewhere. I'm somewhere. It's not terrible. Let's unlock stuff and see what we get. All right. So this is not perfect. I can probably tinker a little bit with it. You can see. So answer to your question, right? How easily does the software get it? Well, I work at this company. I know how to use the software. Took me what, 90 seconds. So not terrible. If you're a novice, it might take you a little longer, but the fit's not too bad. You can see I have some results here, different capacitances, and then I know this isn't a W. If I fit a Warburg, it just takes a little longer in the software, which I'll show you one example now. This is a different kind of plot. This is a Warburg short. I didn't get into that, but it's a finite Warburg element. So that's this feature here. I think in the interest of time, I'm just going to skip right to the solution. I did this already. It does fit pretty quickly, but you can see a W right here. Okay. So that's this feature at the end here. You can see I'll change the value just to show you where it comes from. And this one also similarly, I did a little bit of stuff, but for the most part, it didn't take too long to get to the fit. Now there are times where it's taken a long time to get the fit. It just depends on the data. So it's not straightforward. Unfortunately, there's no real single answer, like how easily does it get the fit? It's like, it really depends. It depends on the software. It depends on how much experience you have fitting, and it depends on the quality of the data and things like that. But generally, here we go. I have a W and I can plug it into, this expression, whatever the A one is, right? And get a value for my D. And so that would be one, I guess, answer to that, or one full, I don't know what you want to say, working through that. So Wojtek, if you have a follow-up, please let me know. I know I've been talking for a little while. I tried to answer this question pretty thoroughly. And I hope that kind of covers all of what you asked. I think I got through it. Anyway, please let me know if you need a follow-up. Otherwise, I will shut up now.
That's all good.
Yeah.
All good. Just trying to answer questions.
Yeah.
The next question comes from Plankhouse, who's asking, what is EMF actually? Electromagnetic force or electromotive force? I think maybe what is it actually, as opposed to I think
what is it in fake?
Yeah, I'm trying to think about it's a force. It's like Coulombic attractive repulsive forces versus negative positive things. I think we might need a little bit more clarification, because you can provide a very detailed answer based on calculus and stuff like that. Like the potential of something
Can't you just say it's potential? I mean, isn't it basically the potential? Isn't it like an older archaic term for potential, or is that not quite right?
I don't know.
My understanding has been that EMF is kind of like polarography. We don't say polarography, we have voltammetry, but polarography was the old terminology for hanging mercury drop electrodes and stuff like that, right?
Yeah.
But it's kind of the same thing. I might be totally wrong, but that's kind of my understanding of EMF.
Yeah,
it's just a potential.
It's just a potential. Well, I guess that's the answer.
Right.
An EMF is a potential.
Yeah, because it's an energy, electromotive force. Well, it's a force.
Well, yeah, and this is where because I've been thinking
down
about
some crazy road again.
I know. I've been thinking about this subject for the last 3 weeks, understanding the difference between potential and voltage. Sometimes these terms are just thrown about interchangeably. So the potential represents the potential, first off, is a potential in volts, and you can think of it as an energy that's required to move a test positive point charge through an electric field from some infinite distance away. So there is and kind of the interesting thing about it, and actually it's almost easier to understand these things based on, it's easier to think about these things from analogy, like water pressure is commonly used, just, a boulder on a hill. So a potential, like if you have a cliff and there's like a boulder on it, that that boulder, there is, quote, potential energy in the boulder falling from the cliff. But until it actually falls and releases its energy, it has just potential. It has the potential literally to fall. And the energy of it is associated with the gravitational force, if you will, and as well as the height. And so if the boulder falls on a hill that's a little bit higher, then it has a different potential between those 2 points. So that's what potential is. It's only when so again, electrochemistry would get into trouble with, like, you have energy diagrams, but then you also have potential diagrams, and they actually represent different things. They're related, but they're not exactly the same. This is getting into,
We gotta,
some other things. It gets into a huge rabbit hole, how deep you want to go into it. So
yeah.
So Planck house, let me know if you want, let's see, actually, what was it? So Chris actually has an answer to this. There's a force associated between charged point particles, and the ability to accelerate an electron in a vacuum is a good visualization. Think about a vacuum tube or a CRT, the ability to accelerate an electron in a vacuum. So yeah, I guess maybe this one it's the force associated between charged particles or charged point particles. So they don't have like a physical volume, sort of say.
Yeah.
And in that case, it's Coulombic attraction and repulsive forces, really. So maybe that's a good enough answer, Planck house. But if you want us to talk more about it, we can. But I don't know.
I think we'll leave it there for now, though.
Yeah.
The rabbit hole will continue
yeah.
ad nauseum.
Ad nauseum. Yeah.
Into greater depths unless we cut it off.
So there's a question from Anonymous Wombat. Anonymous Wombat 16. In a lithium E,
I guess
copper
electrolyte, I'm guessing.
Electrolyte, just random electrolyte.
Yeah, I guess.
Cell. What is the difference in the energy diagrams in LSV for a reduction of the electrolyte at 0.05 volts and lithium plating at negative 0.05 volts? Why won't lithium plate onto copper at 0.05 volts? And then he clarifies to say LSV is linear sweep voltammetry. So there's a difference in energy diagrams. In LSV.
So it's a lithium copper cell. So the first of all, why won't lithium plate onto copper at whatever? So first of all, the potential is with respect to what? So there's that. That's a question. But I think one
Maybe
thing,
it's just a voltage difference between the two.
Yeah, I mean, I don't know precisely what. I guess it's like, just look at this for instance. Like, so the potential, standard potential for lithium reduction is minus 3 volts. Copper's down here somewhere. It's not.
I know they have a super huge list of standard.
I know. I'm just trying to find copper.
And there's also, this has different coppers. That's like copper cyanide.
Yeah, exactly. So I'm just going to make an
2+.
assumption of like copper 2+ or something, I suppose. Where is it? Did I go over it? No, that's copper, like
that's
copper ammonium or something like that. Where is
Wait.
it?
I think
there's copper 2+. This one.
Okay. Yeah. So there's
plus,
that one.
plus 337. So first of all, it's hard to answer this question. I don't know what the species you're dealing with is, what the electrolyte is here, but you can see lithium, copper. So gosh, which one is?
So why won't lithium plate onto copper?
So for instance, if copper's the cathode and lithium is the anode, its cathode potential minus anode potential is your cell potential. So it's like plus 0.337 minus a -3. So your cell potential would be like 3.4 or whatever. Okay, so you have that. And you're talking about 0.05. It's like versus what? Yeah, I guess I don't know how to answer this because I don't know what that's with respect to. And then it's like what is that? All of what I'm talking about too, by the way, is assuming the only appropriate potentials are related to these plating, right? Like copper plating between 2+ and elemental copper, and lithium plating between Li+ and elemental lithium. Now, those might not be the like thermodynamic reactions of relevancy in your cell. It could be something else depending on what your electrolyte is, whatever the cell potential you're measuring is. And so I think it's sort of hard to answer your question because I don't know, precisely what's going on there. And in short, what I would say is that in theory, from what I just showed you, it's like if the potential at the copper. Okay, let me say it this way: if there are lithium plus ions, at the copper side, because I'm assuming your electrolyte has some Li+ in it. Okay, so that's the one thing. So if there's plenty Li+ ions at the copper electrode, and the potential is at that copper electrode substantially less than -3 volts versus NHE, then in theory that reaction would take place. Like this is just standard electrochemistry thermodynamics, right? You don't have a reference electrode necessarily, so what is exactly the potential there?
Yeah, he clarifies to say, so
Okay.
he means that the cell potential. So he's talking about
Versus
Li
Li+.
plus
Okay.
with copper as the working electrode.
Right.
Um,
So okay, copper
So-
as the working electrode. So copper is the cathode, like I said. Lithium is the anode. So what I assumed was accurate. Right. So I think versus Li plus, if you're at a positive potential, so there's two reasons that come to mind. One is that you're at positive voltage. In theory, you wouldn't have a negative voltage in a cell. Like that's, I'd have to think about this because this is an unusual. It's plating. So I actually suspect the reason is more to do with the fact that I don't know what the like.
I think we need to know what the reaction mechanism is.
Well,
I think you need to line up like. So what you did in your head was you took like lithium plus an electron goes to lithium solid.
yeah.
Okay, that's one thing. But then at the end of the day, you need to have a reaction where Li plus electron gives you LiCu. Right? Like,
Well, I think the idea that he's having is he wants Li plus, but it's just the copper's the substrate, and so there is just Li.
okay.
And to your point, that doesn't happen. Like that doesn't happen naturally. Now, I don't know how to explain it from the perspective of the potential in the standard table that I just talked about. But to your point, that LiCu or some kind of species like that
Yeah.
is how lithium fundamentally operates. Like generally speaking, at an anode, or in a lithium-ion battery, I'll say lithium tends to go in and out of both electrodes through one of three mechanisms: intercalation, conversion, or alloying, right? And copper is not a metal or species that functions in either of those three by itself. In fact, copper is usually used as the current collector for the anode in a lithium-ion battery, which means it's the backing metal that is just used to get conductivity to the anode material, which is usually graphite or lithium metal. In your case, it's just plain lithium metal. So I don't suspect you will get any activity. Like there's two things that can happen, right? You can try to plate metal A onto metal B, and in theory, having the right potential is one part, such that the potential at that electrode being in the right area, right, less than the standard potential, reduction potential, is one thing, but not all metals plate on other metals, right? Copper plates on platinum very nicely, but copper doesn't plate as nicely on glassy carbon. It just doesn't. Like you can, I don't think.
Well, yeah, but I still think there's like, I think he's talking about just like the thermodynamic argument of like whenever we look at plating, like one of the first things that I think you're supposed to do when it comes to plating is you're just trying to figure out thermodynamically, you're trying to reduce like, so we're not talking about intercalation or we're not talking about those other mechanisms. We're talking about like over or under potential deposition, right? He's talking about plating lithium just like onto the surface.
Right.
You can also have copper oxide. First off, I think that's another kind of experimental thing. Copper oxidizes actually pretty quickly. You put a penny out on a table over time, it starts to wear. It's not like super shiny. So you may have a copper oxide film. That's one important thing. That's also one reason, and that, you know, that's a spontaneous reaction, sort of say. So I guess my question is this electrochemical cell a galvanic cell? As in you hook it up to, you know, when you hook it up to a load, it'll actually generate power by plating lithium onto the copper. Is that the case?
I doubt it.
Okay.
So again, I think it's a compatibility thing, because like I don't think lithium easily plates onto copper fundamentally. I don't know what the reason is. Maybe it's you know what the like scientific explanation would be something like it's like a lattice mismatch or something
some kinetic issue.
Like for example, like it's like I said, right? If you have a platinum electrode, right, in water with copper sulfate, and you go negative enough potential, the platinum will just copper will plate on the platinum.
Yes.
Right. The platinum electrode turns orange or whatever, because copper just easily forms a layer onto platinum very happily. You can strip it off. You can put it back. You can strip it off. You can do that.
But that's when you're applying a potential.
Right.
Like,
but what I'm saying is that in this situation with a copper electrode, if you go to a negative enough potential, lithium will just not plate on it.
Well, he's only talking about going to 0.05 volts, which,
and I'm saying that
be
irrespective of what potential you go to, it's not going to happen, because it just, not every metal plates onto every other metal just based on potential. There's other reasons, and it has to do with, I don't know, like like the lattice or something, or I don't know well enough how to explain that, but I do believe, like, again, it's like I said, copper will plate onto platinum based on the potential, based on the same potential. If your metal is not platinum, but it's 304 stainless steel, does it still coat? It might. I don't know. Maybe it doesn't. Maybe it doesn't at all. If you have glassy carbon, it just doesn't. You're like well within the potential that you should be plating copper, and it just doesn't. Maybe you form solid copper in the solution, but it doesn't plate onto the glassy carbon. It won't. It doesn't make a film very well. It doesn't stick. It doesn't adhere. It doesn't absorb. Like, I don't know what the reason, you know what I mean? Like, thermodynamically it does. Yeah, exactly. Like Chris says, it plates then exfoliates. Like, it doesn't.
Well, yeah,
it doesn't plate. So lithium might be plating, so to speak, like forming solid lithium, but it's not sticking onto the copper, so it doesn't look copper. And there's reasons for that are outside of the potential argument, is what I'm saying.
Yeah.
And again, I think it's because lithium is used as a current collector, not as a plating material in the scope of batteries, because it doesn't work that way.
Okay. Well, I hope that's enough.
Anyway, I mean, did you have any?
No. I mean, it was just like in the experiment, it's like if lithium is plating and then flaking off, then you should find lithium flakes, ideally.
Yes.
In your solution. That would be a way to
just like
check
Chris,
that.
Yes, exactly. I mean, it depends how much.
Well,
right?
yeah.
I mean, it might be kind of slow. In theory, over time, you would see flakes of lithium form that drop off and sit in the solution or whatever, because you're plating lithium, so to speak. It's just not sticking to anything.
Yeah.
So you might see that is for sure. Yeah.
Anode
sludges in the mining industry, which are recovered and processed. Yeah. It's like you get precipitates, whatever. Yeah. It's nice when the precipitate, so to speak, sticks to the electrode, so you can do stuff with it.
Yeah.
But it doesn't always happen that way. So I suspect that's kind of what's going on here.
Yeah. Well,
so
hopefully that helps.
Yeah. Anyway, hopefully that's a decent answer for their
It seems like Erin is asking, what is the hydrogen fuel cell?
I can show my animation.
Yeah, your animation is very good.
Yeah, I'll show it. Why not? I'll describe a hydrogen fuel cell for you.
Mm-hmm.
Let me share my screen and do this. So here, this is a hydrogen fuel cell, or otherwise known as a proton exchange membrane fuel cell, or a PEM fuel cell. So it typically consists, it's a device that consists of an anode, a cathode, and a membrane. The anode and cathode are usually both platinum, often platinum on a substrate like carbon. The membrane is usually something like naphion, which is a polymer that its job is to shuttle protons. So it has ligands that are negatively charged that facilitate the permeability of protons. They allow ions to pass through and not electrons. So the anode and the cathode are electrically isolated. They are then connected by an external external device, like a potentiostat if you're studying the fuel cell, or a car if you're driving and powering it with the fuel cell, right? On the anode side of the fuel cell, we flow hydrogen gas. The reaction at the anode is simply splitting hydrogen into protons and electrons. This is the easy, quick reaction. This is essentially the opposite of the hydrogen evolution reaction. If you're familiar with the HER, for instance, that's where you combine protons and electrons to form hydrogen. This is just going the other direction. And this standard potential is 0. This is the reference, potential for us as electrochemists. So you can see that the protons split up. They travel through the membrane to the cathode. The electrons travel through the external circuit because they cannot go through the membrane directly. And that's where your electricity comes from. This is an energy generating device. At the cathode, we flow air or oxygen, but oxygen is the fuel primarily. And at the cathode, the oxygen combines with the protons that went through from the anode, as well as the electrons that traveled through the external circuit. And we do the oxygen reduction reaction, ORR. So this is the oxygen reduction reaction right here. Oxygen combining with 4 electrons and 4 protons to form 2 waters. And the water is the only product. And so this is also the rate limiting step, which means it's the slower one, which is why basically everybody is studying the oxygen reduction reaction and not as much the anode side of a PEM fuel cell. You see a lot of papers and stuff over the years on ORR for this reason. Again, the main benefit of this is that the product is water. And so we input hydrogen and oxygen, we get water and electricity, and about 1.2 volts of power, or of voltage anyway. And that is the operation of a PEM fuel cell for you. So
Nice.
there you go. That's the
good.
answer to your question.
All right. Very good. Very good. That was a good question. All right. You have a great animation to describe, like, what's a fuel cell? This is it.
That's a fuel cell.
That's it.
Comes in handy when you have all this material you put together. It's like you with the workshops. You have like a workshop on every possible theoretical topic.
Well, almost.
Yeah.
I'm still wrapping my head over some of these things. I feel like I'm getting closer.
Eventually, we reach the asymptotic limit of knowledge.
Yes.
That was very nerdy.
So we have, as we wait for more questions, there was some questions. It looks like the one guy did come onto the live stream to talk to you about your question originally, right? Or no?
What? Oh, the one from the YouTube comment?
Yeah.
That was Wojtek. Yeah, I
Wojtek.
answered that. That was the one I talked for the rest of for forever about. So yeah, you should answer the other person.
Yeah.
Yeah.
So
water is boring. Make amines.
Amines. Yeah.
Uh,
So this is a question from an email this person called earlier. This is like a document, so I know this is hopefully maybe a little hard to read.
I can see it.
So this is broken up into two big questions, and don't worry, it's not just going to be word salad. There's actually a lot of we have a PowerPoint to go with it. So if you want to provide PowerPoints with some of your stuff, we're more than happy to look at them and provide all kinds of information and curiosity, and hopefully answer some questions. But this is with regard to RRDE collection efficiency and performing rotating disk experiments. So the first question is, what is your recommendation on obtaining consistent, reliable solution resistance measurements based on potentiostatic EIS? So I'm using potentiostatic EIS to correct for the RU in the hydrogen evolution reduction reactions, HER. I always get these acronyms like messed up. I feel like hydrogen evolution reaction, right? But I don't know, but I don't always know which x-axis value to use, since sometimes the PEIS curve will not quite cross the x-axis or double cross it in the same region. So I know it isn't just RU plus RCT from slide 1. I found that even slight variations in RU can impact the apparent consistency of replicate LSV curves. So I'm concerned about really just trying to figure out what is the correct RU measurement. So let's talk about that one first, because each one of these is fairly long. So I'm going to now share this other slide. And let me blow this guy up. Okay. All right. So this is, let me make it a bit bigger. So this is the question. So because this person is doing potentiostatic EIS, and generally speaking, we know that, let me just also make sure I can make comments on it. And we know that if we do
You're not sharing anymore.
I'm not sharing anymore. Oh wait,
Thank you.
thank you. Let me
Unshared.
I unshared.
Sharing is caring.
Sharing is caring. I need to care more. Okay.
Now you care.
And this all kind of comes from how we model the electrode interface, and the fact that at high frequencies we're primarily looking at this region, and this guy is effectively equal to 0 when we're at very high frequencies. But when you actually do potentiostatic EIS, you get like several data points in the high frequency region. So this is kind of a zoomed out picture of the EIS, and you get these data points. And so it's not clear. It's not like it just shows up as one data point. This is your solution resistance. But like, which one of these data points do you actually use? And this person is using different solutions, and they have found that even under slight variations, this is where like they do the LSV, and they find slight variations like 1-2 ohms, maybe 3 at most ohms. This is consistent, but when they just pick one value, you actually end up getting fairly significant shifts in the solution resistance. So they're trying to figure out what exactly is the best way to determine the resistance. So my view, my approach, or opinion is that you don't need to go from 10 to the 6 to 10 to the 2. You can just stick within a much higher, not a higher frequency region. You can go from like 10 to the 6 to say 10 to the 4, because you're not going to need these data points when collecting the solution resistance values. But my viewpoint, at least, is you want to pick values where. So let me at least explain a little bit of what can be causing the problems. Some of the problems are just that other electronic circuits and components and parts in your potentiostat, in your electrochemical cell, can contribute to the apparent RU. So and not just the RU, but what values for impedance do you get at the very high frequency? So you can have cable inductance. There may be other capacitive elements, things like that. So in this view, my thought or recommendation, and Neil, please let me know what you think, is you want to pick the RU where the y-axis value is closest to 0, because any negative imaginary impedance is associated with capacitive values, and the solution resistance, which is ideally the ideal only resistance that you should be getting, should have very little to no phase shift, because an ideal resistor doesn't have a phase shift associated with it. It doesn't have any imaginary impedance. So in this point right here, we see that there's about 7.5 ohms of negative imaginary impedance. It's like, oh, well, this one, it's not entirely RU. It also has contributing factors from a capacitor or something like this. And if I'm looking at like these 3 data points who are all here, I might pick the one that's I might pick this guy because it's like 25. It's a little bit closer, but there may actually be a point somewhere in between here that's earlier. So that's kind of my view. You want to pick something where if you were to look at the Bode plot, you'd have something where the phase angle was like closest to 0. And that's not always at the 10 to the 6 hertz. It may actually be lower. It could be 10 to the 4 hertz or 10 to the 5 hertz is where you actually see a phase angle that's closest to 0, and that would be your actual RU in your system. Any thoughts, Neil?
Sure.
Sure.
So everything you said is correct under normal circumstances, and in general, that is exactly what you want to do. Limit the range of your impedance to 10 to the 6 to 10 to the 4, maybe 10 to the 3, whatever. You don't have to really go any lower than that. And picking the point that has the lowest phase angle closest to 0. It doesn't, especially if your data are not crossing the 0 y-axis point, the phase angle will never be 0. It might be, minus 5 degrees at closest, or so, so whatever, or 5 degrees, lowest amount number. So that being said, let me illustrate something for you.
No, I'm stop sharing.
That with your specific data, with the potentiostat that you're using, okay, first of all, also the other general answer for you to get a consistent measurement, I'm not trying to be funny here, consistently to get the result is to choose a method and use it consistently. So whatever technique or criteria by which you choose the RU, apply it equally across all of your impedance data, because you're using the same potentiostat with the same oddities, if you will. And so you want to use the same criteria. Don't be arbitrary about it if you want to be really serious. Now, there's 2 kinds of data that I'm seeing with your potentiostat. This is pretty common for this particular brand of potentiostat. At the highest frequencies, we have what are called artifacts, weirdness, stuff that doesn't really correlate with reality. You have 2 options. One of them is it does this. I'm going to draw it over. It would be in the same spot, but hopefully you understand. The other is where it's doing this. All right. Now, with the red one, this point right here is both the lowest phase angle as well as the sort of inflection point between all of this stuff, which is nonsense. All of these data points are garbage. This is not real. This is not from chemistry. This is not from your material. This is not from your electrolyte. This is not from anything. This is from the potentiostat, from the reference electrode, from artifacts within the circuitry. None of it is to be acknowledged, just be disregarded. So this inflection point is both the point at which the phase angle is minimized, as well as probably the point where you can take your RU. However, if you do the same with this blue curve, which is what seeing in some of them, you might take the point here or the point here. That is not a good idea. These points are part of the nonsense of disregarding. Okay, so I would pick somewhere around here. You want to pick roughly so one metric by which I'm kind of advocating is not necessarily just where the phase angle is the smallest, but roughly where ZR is smallest, right? It's the point that's most this direction, generally speaking. That's one metric by which you can do it. I'm not saying that's exactly what you should do, but it's one option. The second option that I would suggest involves circuit fitting. So let's say if you do the whole 10 to the 6 down to, 1 hertz or something, you might get like, whatever, you get something like that. But if you just do, and then there's, whatever, there's stuff up here, right? And let's say you just take Alex's advice and you do like 10 to the 6 to 10 to the 4 hertz, right? I'll zoom in a little. You're going to get, you get whatever you get for the curl stuff, and then it's going to be just kind of this part of the curve. You won't even get a semicircle. And just like Alex said, this in a very simplistic manner is your circuit, right? You have a RC void element for the HER and the RU here. And at the highest frequencies, you're just studying this, basically. So one option is to take your data here, neglect some of the high frequency stuff until it sort of turns the corner. There's some subjectivity here. I understand that. Fit this circuit to it. And whatever you get for RU, that is RU. And so there will be some fitting, and it might not be fit a CPE, by the way. Don't fit a capacitor, because a capacitor, well, I guess I shouldn't say that.
It won't be a straight line.
You can make that call. I shouldn't say definitely fit a CPE. I would probably fit a CPE. Yeah, what you're going to find, of course, PowerPoint is having a stroke because I decided to get rid of lines. What is happening? So, really? Yeah.
Sorry.
I'll open it again.
Also, Chris makes another good point. He also said it might be worth checking your instrument against fixed resistor values just to ensure you don't have any inductance or capacitance issues. So use physics, like just put a resistor across your potentiostat, and that would be another way you can actually check its how accurate it is when doing measurements.
That is a good point.
Good piece of advice.
But my point here is that if you fit, right, either that or CPE, right? You'll either get a fit that was, if you do the capacitor, the worry is that it'll be an averaging kind of a thing, and it's going to be a straight up and down line. It might, sort of miss the value. If you allow for a CPE, what you'll probably get is like a straight sloped line that will extrapolate. I'm trying to draw a straight line here and kind of failing, but it might extrapolate, wherever if this is 0 here, I'm just, you might extrapolate to something like that. And again, which is correct. I mean, you could use the point here, the exact value and the point. You could use the extrapolated value based on the fit that I'm advocating for here. It doesn't really matter. Although I grant that part of what this person's telling us is that they are seeing that it matters depending on which one they pick. I think the key again is that choosing the same methodology at each solution, at each situation, choose the same methodology and stick with it. So at least you have consistency. So if there are, the worst thing you can do is pick a different methodology and have the errors of unknown origin propagate in an unknown way. It's like if you pick the same methodology, at least if there's some error, let's just say it's consistent across all of your tests. And then you can pick a different methodology. Like you can even you could apply it afterwards and like do the green method. So apply this to all of them, and then instead do this, and then see how that adjusts the data, and then pick which one objectively seems to be more accurate, if you will. I don't know. You could do stuff like that, right? But those are my suggestions for that. And mainly, again, the key is you want to try to avoid relying on data points that are within that curl at the highest frequencies. That's just not, I would be very hesitant to pick a point where it's going backwards, so to speak. Those points don't really relate to reality. It's like circuitry, artifacts, reference electrodes, stuff is getting in the way. It's not really related to your potentiostat, to your solution resistance much. So I would be very hesitant to rely on those data points, to be honest.
Yeah, those are great points and things that I don't always think about. So that's that. So that's the solution resistance. Do that.
Do that.
And then the second part, actually, let me share the other part of the question. I was just gonna jump straight into the slides, but I think it's important that at least we we read a little bit. The second question is, why wouldn't RDE produce HER data that exhibits the variable scan rate dependence that she shows in slide 3? And I will talk about what those things are. So I've had a little bit of time to look at it. You sent it to me a little bit, not late, I would say, but like a couple hours ago. And so what this person is observing. So this is RDE data, taken at one scan rate in different, slightly different electrolyte solutions, and what they're doing is they're doing different scan rates as they rotate, and they're choosing different resistance values, R1, R2, and R3, just as we discussed. And so this is the case for water reduction. This is the case for bicarbonate reduction, and then we have proton reduction. So one thing that is, and one thing that we observe, or that the person observes, is that as they increase the scan rate, going from 20 millivolts per second to 200 millivolts per second, there seems to be very little overlap between these curves. Conversely, when they increase the scan rate, there seems to be overlap between these curves, and they see an increase, some overlap, as they increase the scan rate for H plus reduction. So you get somewhat of an inversion going from going between these as they change the scan rate. Now I mentioned that in the previous live stream that you want to ideally do RDE at you ideally want to do it at as slow a scan rate as possible. RDE is not designed for these fast scan rates like 100 and 200 millivolts. Even 20 millivolts per second is actually fast. RDE is supposed to be a steady state reaction. You can just do a chronoamperometry experiment and literally take one data point at a time, and you should be able to get these same curves. And when you start to scan at fast scan rates, you deviate from it, and you can even see, or you would see, that if you go to very, very fast scan rates, your LSV curves will start to look more like voltammograms, and have characteristic signals of voltammograms, which include capacitance or double layer charging, things like that. So this is an interesting and kind of unusual phenomenon to see, like, oh, you get these weird kind of like, there's no overlap here, there's some overlap, and then like there's a little bit of overlap, or like it kind of reverses, if you will. And there are a couple things that I would mention about these plots. Some of these are questions. Some of these are questions and points of clarification. So one thing that I noticed is that I saw an E minus IR versus RHE. So E minus IR is not a typical plotting convention, sort of say. We just do E versus RHE, or versus your reference electrode. So that and in the previous slide you had mentioned, you talked about the different resistance values that you used. So this begs the question, which is, are you using IR compensation? So it's not just doing IR compensation in post-production, but a potentiostat has the ability to compensate during the experiment the potential, right? So one question is IR comp on for these experiments? I'm not really so sure, because some of the data actually will make a lot of sense if IR compensation is not on. Because one thing that's particularly interesting about this water reduction is it's not really so much that, there's no overlap. It's more that the onset potential keeps getting higher and higher as you increase the scan rate. that is actually probably the more interesting result about this water reduction. If we look at this, um, the y-axis scales are fairly different between these three. So for H plus, we got 0.05. I'm assuming these are the same units, milliamps per square centimeter. But like this is 0.05 milliamps per square centimeter. This is 0.4 to 0.8 milliamps per square centimeter. And here we have like 20 and 40 milliamps per square centimeter. We have huge differences in the magnitude of the current. So when you mentioned earlier that, oh, you're actually seeing huge deviations in the IR, in the solution resistance, it's changing your results. Well, that will be in big part to how large the current is. So from that standpoint, oh, what just happened? Oh, I just
You
something
stopped
just
sharing.
I stopped sharing for some reason.
Hmm.
Maybe I accidentally clicked on something. Oh, my
Did your thing die like mine did?
yeah, the PowerPoint just died. I have my thing charged up. Okay, yeah, so PowerPoint just died for some reason. That's okay. Because nothing. Yes, document recovery closed.
Just happened
Okay,
to me
so
too.
I'm
I
here.
guess it's contagious.
It is contagious. So is IR compensation on is one of the big questions, because that's the main thing. That's one of the big things I'm noticing here, is that there's a shift. And this shift makes a lot of sense when you consider when we're moving to these very high scan rates, that we're pushing the potential. You're getting more current, so your IR drop is higher. So the potential where a process is occurring is much higher. And it's also noticeable just if we even look at the 20. I'm going to erase some of this just so that it's clear. And I'm going to zoom in a little bit here, because it's really this guy that is the kind of the thing you mentioned that was kind of confusing. But if you'll notice, even at 20 millivolts per second, the same scan rate. So we're just looking at these three here. The same scan rate, there's a sizable difference in the potentials between these guys and how they're moving, all at the same scan rate. So, and it only varies by what resistance value was used. And so that leads me to think that IR compensation is not necessarily turned on. I'm not 100% sure, but it's an explanation as to, oh, you're getting this shift partially because as you move to faster and faster scan rates, you're getting more current. Current times the resistance is also pushing the potential further. That's a hypothesis, without knowing more details. And you did send me some extra data about it, which is very helpful. But that was one thing as I was looking through this, I thought, oh, I don't actually know if IR compensation is turned on as a thing. So that's kind of my comment, because this amount of current is much higher than these, and that's why, oh, you don't see this. And when you do have faster scan rates, you get more current associated with double layer charging, and double layer charging absolutely is much more observable in these smaller current ranges when you're going to faster and faster scan rates. But here you may be observing a bigger impact on the IR drop because you have higher currents in this water reduction region. So that's, I guess, a question, but a possible explanation as to why you're seeing this behavior. And the last point that I'd like to make is, I do think that doing these experiments at very slow scan rates, I mean, 5 millivolts per second, even though these take a long time, um, is the proper way of using a rotating disc electrode, because it's supposed to be a steady state process. And if these, water reduction, I'm imagining, I think you mentioned this was like a silver electrode. I don't know if it's a silver type of catalyst, but if it's a slow catalyst where the heterogeneous kinetics are slow, um, then it could be the case that stuff is is not happening. You're not achieving equilibrium quickly enough as you move to these faster and faster scaling rates. So that's another like element of this whole thing that I think is very helpful, or that would be helpful to look into. So that was my kind of 2 cents on that. So hopefully this is helpful, and it looks like we may have got some extra questions that have come in the meantime.
Well, Chris made a
possibly.
couple of comments.
Oh, yeah.
I guess this is about the last one. So just one of the points he made, which was that about higher current densities, you might have other stuff happening too.
Yeah.
And maybe it speaks
Mhm.
to the last point you made, which is that, you know, if you have slow kinetics or other speciation or other sorts of reactions going on, that might be leading to the observed
Yeah.
effect. But yeah, absolutely, you want to try to scan as slowly as possible, especially
Yeah.
if you're up against slow kinetics. You definitely can't be scanning
Yeah.
too fast. You might be stifling your own experiment, so to speak. So
Yeah.
Bill Clinton has a question that looks like it was typed into an AI program, or just someone typed in, ask a very sciencey question into an AI program. And I'm wondering if that's what's happening here.
How do long-range electrostatic correlations and ion-specific adsorption modify the potential of zero charge beyond mean field Poisson-Boltzmann predictions?
It just looks like it was either an exam question or something that you typed into ChatGPT. Give me a question with smart sounding things of electrochemistry or physics or something. I'm not, as best I can tell, what it is in theory asking is the Poisson-Boltzmann equation describes the field effect away from the surface of an electron, electrode, which is like the chart you've shown a million times, right? About how the field,
about the double layer.
yeah, like how the field drops off or whatever away, and then electrostatic correlations and ion specific adsorption modify the potential, or how that, like I am.
But the potential of zero charge.
Yeah.
So he's talking about I'm assuming he's talking about the potential where the potential of the metal electrode is, quote, equal to the potential of the solution that you have in your system. So when those two things are kind of equal to each other, ion specific absorption. I'm going to
I think we leave this one.
Yeah, I mean, Bill, I might just have to say I don't know the answer, or it's a little bit.
It's a convoluted question that probably has a convoluted answer. And apologies if this is a good faith question, but I suspect it is not.
Okay. Sorry, Mr. President.
The phrasing and the grammar and the punctuation looks like it came from an AI program. Just gonna call it out. It's what it appears to me. So if it's a real question, then my apologies. I'm not sure we can really fully answer it very well, but I don't suspect this is a real question. That's just my opinion.
Okay.
It's a bit much.
Do we want to answer? There was a question before about what if we can explain the Nernst equation.
Oh yeah, that's a good one because it's your favorite.
That's my favorite.
Yeah, I totally forgot. Yeah, Aaron asked, "Can you explain the Nernst equation?" I think you should definitely.
Okay, I'll just explain it.
Aaron, you have asked the perfect question because it's Alex's favorite equation.
Yeah.
Because everything in electrochemistry, as he's about to tell you, comes back to the Nernst equation.
Yeah. So can everybody see?
Yeah. You're good,
okay.
You're good.
So, well, actually, wait. I have the Nernst equation here.
Yes.
So this is the Nernst equation. I know it's like we explained this a lot, but when the let's see, let me get to my inking. When the Nernst equation basically states that for a given redox reaction, so if you have an oxidized species plus an electron, is in equilibrium to form this reduced species. It states that the potential difference between the metal and the solution, but the potential is equal to the standard potential. Sometimes it would be the formal potential if you're not under standard conditions. That's when the temperature or the pressure are different. Minus RT, these are RT is the natural gas constant, T is the temperature, N is the number of electrons transferred. In this case, it would be 1 for 1 electron, and F is Faraday's constant, times the natural log of the activities of the redox species and divide by the activity of the oxidized species. Sometimes we'll use concentration instead of activity, but the technical definition is activity. And this can be thought of or interpreted in several different ways, which is to say, you can use at equilibrium, you can use a external power source like a potentiostat or a battery to change the relative concentration of these two species. Conversely, if you were at, say, an open circuit potential and there was no power being pumped into the system, you could change the electrode potential, this difference, by just adding more of the reduced species, and so or changing the concentration of the oxidized species in this system. And this equation is very useful because during cyclic voltammograms for reactions that have fast kinetics, so it's assumed this is an equilibrium. This is assumed that, like, if you're changing the potential, this rapidly changes. Then in that case, you're able to extrapolate useful information in like a cyclic voltammogram, and you can get current to flow at the electrode surface. So this this equation is valid primarily at the electrode surface when doing electrochemistry experiments. So there are ways of deriving this equation from, like, there's ways that you can take this and derive this equation from other things, and we can go into more detail of it. But that's the way. That's kind of like the best way to think about it. That's how I at least think about it, because this term and these, they're all kind of loaded. And then also, as Neil likes to point out, for the most part, these are effectively concentrations. So if you, within a certain range of concentrations, these are equivalent. If you go beyond the range, they start to fall off. But that's it. That's the Nernst equation. So if you have any follow-ups about the Nernst equation, please let us know.
Very good.
Mm-hmm.
Garda viewer has a very general question. How does somebody become a good electrochemist? I'll let you know if I find one.
Mm-hmm.
What makes a good one, and how do you become an expert at a technique? Well, I mean, the simplest answer is graduate school. We
that's at least part of it.
That's part of it. Yeah. I am a firm believer that you don't have to necessarily go to school to become an expert in anything if you wish to study it and obtain materials on your own. There's quite obviously a benefit in the institution of universities and graduate schools because there's research labs and there's equipment and money for, if you're going to learn electrochemistry on your own, that's wonderful. Hopefully you have like $250,000 or pounds or euros to buy lots of equipment, because a lot of the practicality of becoming an electrochemist involves using expensive equipment, which is why the institutional umbrella in graduate school of universities of a company is often needed, right? But I think that on a philosophical level, or if you will, how do you become a good electrochemist, or how do you become an expert? It is really the same way that you become an expert or proficient in almost any discipline, right? It's learning from your mistakes, being willing to make mistakes, and simply putting in the hours, putting in the time, recognizing, one of the things I guess that I've carried with me since my time in graduate school and as a postdoc is that someone told me this once upon a time, and I observed it to be true, and I sort of keep saying it and carrying it forward, which is that the more that I learn, or in graduate school, the more that I learned, and now even in my job now and in these kinds of live streams, the more that I have learned and continue to learn, the more that I realize how little I actually know. The idea is that as a PhD or an MD, whatever your proficiency is, it's important to remain humble. It's important to remain cognizant of the fact that there's still so much that you don't know. And the more that you do learn about a subject, like Alex and I do this all the time, right? Like even just here
Yeah.
in our office, right? Like we have 2-hour conversations with one of us standing in the doorway of the other one's office, like talking through what's current or what's potential or what is a reference. Like we still talk about this stuff, and we still like have epiphanies together as, you know, relatively mature, you know, whatever, PhD electrochemists. Like I still feel like I'm learning all the time stuff that just never occurred to me before, or like, you know, we talk through a complicated concept that like I never thought of that way before, and I'm like, it's still exciting to me now. Even now, after all these years, I still get excited when I'm like, I feel like I understand this in a way I didn't before. And so that attitude, I think, is really critical in becoming what you would call, right, an expert or being proficient at a technique, whether it's electrochemistry or otherwise. I don't know if you want to add anything to that, but
I think one of the, I guess we haven't actually defined like what makes one good. I'm thinking about that same part of the question, like what makes somebody a good electrochemist? Is it the fact that they know electrochemistry very well? Can they teach electrochemistry well? Do they do experiments very well? I think if you were to put two people in like a room and told them to perform a cyclovoltammetry experiment, you know, the one that completes it better or gets results that are closer to the quote actual one, is that the better electrochemist? I think we can also say that, you know, when you're a first or second year graduate student, you're quote maybe not a good electrochemist, but then by the time you're a third, fourth, and fifth year graduate student, you become a better electrochemist. And so what's the difference between those two? So yeah, those are things, but at the same time, it's like once you've defined what is good, you know, I think the answer is just what Neil said. It's just asking lots of questions, trying to understand things better, practicing electrochemistry, doing it. There's the technique, and yeah, I think it literally is just kind of like hours and time, and yeah, as Neil said, the more you know, the more you don't know, which feels like a constant. It's like a constant struggle, sort of say with us, because it's like once we learn something,
it opens up more questions.
It ends up creating more questions. So, but yeah, I guess that's kind of my, yeah, no, I don't have anything. I just keep. I don't know. I don't even really consider myself a good electrochemist. So I'm like, you're asking the wrong person. I don't know. I'm a terrible electrochemist. Like, I'm not an academic researcher. I haven't like written a book on electrochemistry. You know, it's not like I'm publishing tons of papers on electrochemistry. Am I a good electrochemist? Maybe it's an argument.
Well,
so.
you're running a live stream.
I'm running a live stream
that suggests you can answer questions about it, which you do every week. So I would say you're a good electrochemist.
Well, thank you. I appreciate that. Well,
but it is true. I also feel that way. I oscillate on this myself the same as well. And it's like, but that's the humility thing that I'm talking about, because in all seriousness, it's like, I have days where I feel like, oh, I'm killing it. I'm doing so good. Or like, especially after we've had some of these conversations and we're like, oh man, I understand
this thing.
Matshotkey like I never did before. And I'm so happy. I feel like I'm so smart. Yeah, I get it. And then other days I'm like, I'm the dumbest. I don't even deserve my job. Why am I here? You know, you have days like that, right? You just feel like even this Bill Clinton has said this is not a joke. So my apologies for assuming this question. It's so heavy with terminology, and so that you're studying electrochemistry.
Like really break it down.
I know it's quite a lot, but here's an example where I feel like do I know anything? I don't know how to answer this question. I really don't even quite understand the implications of it. You have ions absorbed, and how is it affecting the potential beyond Poisson-Boltzmann prediction? Like I don't even quite know how to tackle it. And my answer is the same. It's sort of a non-answer. I appreciate you clarifying that it is an earnest question. But it's moments like that where your humility needs to kick in and be like, am I even good as an electrochem? I don't know the answer to that question. I don't know how to do this or that. So I think that to a certain extent, that attitude is necessary, because once you accept once you look in the mirror and you're happy with what you see, or you're satisfied, you've lost. You've accepted that there's nothing more for you to learn, and then you will stagnate intellectually, personally, and professionally. There's always more that you can learn, grow, understand in general, and especially in a discipline like electrochemistry. So, challenge yourself to keep pushing and keep learning, keep asking questions.
I'm looking at Bill Clinton's question, trying to understand.
Oh,
There may be
yeah.
an answer. It can come back to me later about this.
Yeah, if you want to take
I'm
a
gonna-
stab
I'm
at it,
gonna
you
think
can.
about
I'll
this
look
a
at this
little
one
bit.
here. Michael Joyce has said, doing some work on a supercapacitor material, and I have a log plot of peak current versus scan rate to compare diffusion and adsorption control processes. Is there anything I have to be careful of with respect to error bars? So you're looking at peak current versus scan rate. I assume you're sort of doing, was this the radial subject? Randall's, hang on. I just want to think about this in terms of an error bars thing. So if you're making a log plot, peak current versus what scan rate? To compare diffusion and absorption. Okay, so this is a little tricky. The way I learned this when I was an undergraduate is quite complicated. I don't know if I want to open a can of worms. I got to think about this for a second. I know what you're saying with error bars, because like let's say you have an error bar or an error, a plus minus of the current, right? It's plus or minus 1% or whatever, based on your potentiostat, based on your measurement precision or something like that. How does that propagate when you take take the logarithm? Like, is it the same error? Is it still 1%? Is it different? I learned it as I'm going to talk through this maybe, and then hopefully I get somewhere. But I learned this as it's a derivative. It's a derivative process. Let me think. You take the partial derivative of your equation with respect to each variable to get its corresponding error. It's been so long. This was from undergraduate, which I'm very old. This was a long time ago. Let me just sort of think through or kind of walk through this a little, and maybe this helps you. I don't quite know exactly which equation. If you're using the Randall-Sevcik equation, let me just like snap it here. You probably have it in your slides, but that's okay.
Oh,
I got it. It's fine.
We also have the useful equations thing that we saved.
Yeah, that's true. But I'm already committed to this stupid way of copying it from Wikipedia into PowerPoint. I'm committed. It's too late.
Okay.
Yeah, I should have done it better. So, okay, let's just say this is the Randall-Sevcik equation. I don't know if this is what you're using you're taking the log of it or whatever, but gosh, I know I'm sort of oscillating a little bit on this, but the way that I kind of learned this was something like, if you have this, if you want to have like delta I P, it's something like D what is it? It's like the partial equation with respect. Oh man, I don't know if I can remember exactly. You take the derivative, and so it's like basically most of the stuff becomes a constant. But it's like if you're trying to get the error of like scan rate, right? Forget about this. If you do like delta, the scan rate, it's like it's D F D nu or something like that, and so like all this stuff is a constant, right? And then you're taking the derivative of the square root or something like that, so it's like 1/2, something like that. I don't know if this is right. There's something like that. I think I'm going to stop because I can't quite remember. I think that's kind of what you're asking, Randall Sevchik. If there's a weird scaling with the scan rate. Yeah. Okay. So there's two things here, right? If you're talking about scaling with scan rate, there might be something where the errors are in a more simple way. Forget about the kind of complicated calculation that I'm trying to remember on the fly and not quite remembering well. The error is probably in like the specifications for your potentiostat, right? And I very much doubt that it is scan rate dependent, but it's something where like a lot of times the error of the potentiostat will be with like at a current range, it's plus or minus 0.1%. Like, I don't know, let's just make it up. Like it's plus or minus 0.1% at the 1 milliamp current range or something like that. And so just what that means is if your current is higher, the error is higher, right? Something of that nature. So by scanning faster, you're not necessarily making it have more error, like because of the instrument itself. It's just that the measurement is a larger value, and a larger value means a larger error. Hopefully that kind of makes sense. So it's just it's somewhat of a consequence of that. But what I was trying to kind of show, and again, I can't remember. I probably have to look at my old does error scale weirdly with scan rate. I think it's more about your peak current will scale with scan rate, and the error associated with your current is let's just say in the most simplistic manner, the stated specifications of your potentiostat. Let's just put everything else aside. There might be other contributions, right? But let's just say it's like plus or minus 1%. So great. So it's plus or minus 1%. Or the error is you do the test 5 times and you get a standard deviation, like 95% confidence interval, whatever, of 5 measurements or something, and that's what you can use as your error bar. Like there's multiple ways to handle this, and so it will only again scale with scan rate if the measurements become less accurate, because it's just the faster scan rate can sometimes lend itself to that, or because the current itself is getting larger. And so the absolute error is getting bigger, but the percentage wise, the error is not, right? 1% of a milliamp is bigger than 1% of a microamp, but proportionately it's the same. But absolutely it's larger, like 1% of a milliamp is bigger than 1% of a microamp. So as you scan faster, you might end up with a larger absolute rate of error. But I would have to dig in later and try to figure out the other thing, because again, I did this when I was an undergraduate in an engineering class. There's a way to propagate like and in the Randall-Sevchik equation, like I showed, it's like with not with F and like constants or whatever R and whatever, but like T, it's like 298 Kelvin plus or minus something, and they all have a delta plus or minus, and it's a long thing where you can calculate the error that way, and it's a partial derivative thing, and I can't quite remember. Find the potentiostat worksheet. That's probably the quickest way to do it. And propagate that with the material. That's probably the best way to go. Yeah. And the op amp will have a limited slew rate and frequency dependent. So some of that is hopefully built into what the potentiostat manufacturer will dictate as it's like downstream. You know what I mean? What you're talking about, Chris, is more of an upstream. The op amp and a lot of the circuitry will have its own error, I guess, right? But ultimately, what as a user you need to know more is that it's telling me I have 500 millivolts, 2 milliamps. What is the error on those measurements? And so a lot of times you can hopefully use the potentiostats measurements there. And so you could have error bars for both axes, or just sometimes you just have one. It depends. In theory, you would have error bars everywhere, but not everybody shows it that way. Kind of depends on the researcher, I think, in a lot of cases. But anyway, hopefully that's decent stab at that answer, Michael. Like I said, there's some answer to that I can't quite remember well. I'll have to pull up my old undergraduate notes, and I might do that later. try to remind myself of that process just for my own edification. But anyway, we can move on.
Mhm.
Did you have anything to add about the previous thing or no?
Yeah, I can talk a little bit about Bill Clinton's thing. I did a little bit of look because some of the terms like. It's like I've seen pictures of Poisson-Boltzmann distributions, but I never identified them as that. But generally speaking, I think what he's talking about in this question is there is so you have, and of course, correct me if I'm wrong, but this is just my interpretation of it. I mean, the Poisson-Boltzmann equation and distribution describe the potential. So you have this like potential axis. So you have distance from the electrode, you have potential, and what you end up getting is something like this, where you have like, this is the potential of the metal is here, and then you have the potential of the solution, which is here. Oh yeah, these are always superscripts. I always write them as subscripts for some reason, but they are technically superscripts in all the books and everything. And usually there is some kind of distribution of, or there is a field, a field effect, in the sense that the potential changes as you move between these two potentials as a function of distance. And we generally refer to this as like the electrical double layer. And you have certain at certain distances, you have definitions of what's like the inner Helmholtz plane, and then you have something that's kind of like the outer Helmholtz plane, and these are defined as like the distances of like closest approach for like an electrode material, or like a redox molecule to actually get an electron, to have electron transfer. And then you have stuff like, this is like the diffuse layer, and so the ions in the diffuse layer and the charge in the diffuse layer is different than that of the bulk. And it's also interesting to note that the potential from like here to here is the same for like moving an ion. This is assuming you have like a completely charged, not charged, but a high concentration electrolyte, at least 0.1 molar or higher in water, so that it's easy for charge to kind of move back and forth. There's no potential difference between them. And Bill's question, there are kind of several situations when, so this is my understanding, when phi m is equal to phi s, that is the potential of zero charge. So just potential, and I think they just have a zero charge. So I think that's when those two things happen. That's when, quote, there's a net neutral charge, if you will, between these two, and there is no potential difference between them. Of course, you can have potentials that are higher, right? You can have potentials that are higher than the solution potential, and it drops off. So his question is talking about like, what are the effective long-range electrostatic interactions? So that, in my mind, makes it sound like there are ions either over here, or you have a weak electrolyte. And this, I'll use a different color to make it a bit easier to see. Or your field extends out something like this, which is the case when you have weak when you have a low concentration of supporting electrolyte. And then the other part of the question is ion-specific absorption, modified potential of zero charge. So when you have ion-specific absorption, you're talking about, I mean, to a degree, you're really just talking about, I mean, this picture just shows you the potential. It doesn't tell you anything about the ions that are here. But, this is made up of like, oh, there's like minus, and then there's like plus on the other side, and like how dense they are, or how closely packed. So you're looking at pictures of like the double layer. So my thought, or at least answer about how do they modify the potential of zero charge? So how does stuff that happens over here, I think, affect this situation, or as well as ions that are stuck to the surface, affect this beyond what is predicted in the equations of the Poisson-Boltzmann predictions? And I think, the answer is, frankly, I don't know. I'm making up a lot of stuff, but I think that people usually assume the Poisson-Boltzmann predictions are correct, and that other things have to adjust to it. So I don't know if there's like a correction factor or anything like that in the equations, because it looks like, if I look at the equation, it's like, oh, it's just like the charge times the species. Well, if you have a thing that's irreversibly adsorbed, you just add a charge times the concentration of it, and whether it's absorbed or not. And there may affect the solvent permittivity, so maybe there's a permittivity factor in there. But I feel like it doesn't affect the equation in any way. I think that this is just, I think the equation stays the same. And if it's anything, if you want to know about, say, how does this line change, maybe that's the real question you're asking about. Like, how does this line change? Well, this line goes away when you're at this, because these two things are equal to each other, and hence there's no field. It's as if this is here. I mean here. I keep making a subscript for no reason.
There's a good reason.
There's a good reason.
I guess
because most things are subscript. Most things are subscript.
Yes.
We rarely get superscript.
Subscript's the way to go. Yeah.
So Bill Clinton, I hope this is at least my interpretation, my thought about this. I don't know. I've been thinking about these things over the last few days, but not within this context. So, but hopefully that's helpful. I don't know if it really is helpful. Yeah. Sorry.
It's a bit complicated, is what I would say. So
yeah, you need to.
There's a lot there.
Mean field Poisson-Boltzmann predictions. I don't know, because the Poisson-Boltzmann predictions all, like, it just gives you the field. I mean, that's ultimately we get. There probably is an answer, but it's like heavy in the physical electrochemistry field that I don't know enough about. Okay, I think that's all I'm going to say about that. Do we have time for the last one? Or
yeah, I think so. I was looking at some PICKIT stuff because I saw a GITT question. I don't know if there's any more. If there's anything, I think there isn't anything else. Sagar had a question. Doing a DFN, I assume density functional theory. I don't know what DFN. Anyway, modeling of
density functional Nutella.
Numbers.
Density functional Nutella.
Nutella.
I want to have Nutella.
It's definitely Nutella. Anyway, doing modeling of an NMC cylindrical cell. So how do I correctly simulate the rest phase instantaneous voltage rise just after a pulse discharge test during basically a GITT test? How do you simulate the voltage rise? So what I have is, I can talk about GITT a little and maybe it helps answer the question. So what it is related to the phenomenon where I think with GITT and maybe with PIT too. Let me share this. I can't remember which one. Yeah. So with GITT, you have that kind of phenomenon. Now, whether it's the potential, I think you had it sort of the opposite way, where you have the potential rise if during a discharge test. It does, so if it's a charge test, the voltage goes down, but it's the same thing, just in a different direction. Right? This is the opposite of what you talked about, right? This is during a charge test, applying a current, and then it discharges down or whatever. So either way, same kind of thing. The short answer is that you can, oh God, no, that's not right. It's not really the Cottrell equation because you're not applying a current. It's open circuit potential.
Oh, he tells us it's NFN is Doyle-Fuller-Newman model, which I think it's still
Fuller-Neumann.
I think it's still just a model. That
Yeah, it's just a numerical model.
in my mind, it's like, oh, it's just a thing that you plug into a computer to get something.
Well, there's that. Yes.
There's that.
Let me think. I don't know if I know precisely the mathematical equation or relationship that describes that curve. Is the point, right? The open circuit. What would it?
Wait, what describes the open circuit?
Well, so the open circuit, when you're doing a GITT, right?
Yeah,
you're applying a current, the potential goes up or down, whatever, right? And then you release it, and because of like IR drop and stuff like that, the potential relaxes for a bit. And so what dictates this part of the curve here, right? Like this relaxation. What? Because it's Cottrell-like in that it's a decay, but it's I equals 0.
Yeah.
So is it the Cottrell equation?
Well, so Cottrell, I mean, it's similar.
Yeah.
It's like you do a potential step and you watch the current decay.
Right.
There is something I want to say it's the Sand equation.
Sand equation.
Yeah, which
can't you just use the Cottrell equation? And I'm sorry, I'm thinking out loud,
but the Cottrell equation relates the current as a function of time.
Oh, not potential. Yeah, this is potential.
And so in this case,
forget it.
But at the same time, the sand equation, because this is for a chronopotentiometry experiment where you do a step current and you measure the potential with time.
Yes.
And so I looked at the sand equation. It's very similar to the Cottrell equation. It's like, but it has this I times t to the 1/2.
It still has a t to the 1/2. It's still a square root kind of a dependency or whatever, inverse square root. The only reason I was bringing this up was because it just made me think about, again, it's not exactly the same if you're trying to model the behavior, but like one of the things you do with GITT is, and it's something that like our software does, this is why I kind of know about it, is that you can get the diffusion coefficient from some of those curves. Now, it doesn't help you simulate them, but if you have them, you can basically do this. So the this is dE dQ, the change in potential with respect to charge, and after each active step. So this is the change in potential with respect to the time. So there's a weird thing here. Basically, when you're doing when you're doing GITT, you are, let me check. You're getting the diffusion coefficient from the active data, so it's not the same. With PIT, you're getting it from the rest data with PIT anyway.
You can also, one thing that's always related to diffusion, and like if this is a diffusion control process, whatever your modeling is, you tend to observe a 1 over the square root of t. T being time dependent. So whatever you're doing in your modeling, if you relate it, if you're applying it versus 1 over the square root of time, that may be a quote fit, if you will, to the decay. So as time goes on, it's 1 over square root of t, and there's some constants that are involved. But as time goes on, it's like it's going down substantially. So that may be from the NFN modeling, a way of thinking about it, at least to a point.
I think the question is, what is the actual equation? And you're right, maybe it's a sand equation, but it's probably this, it's some kind of an inverse square root of time, but what the equation is precisely, I don't 100% know. Yeah. Anyway, what I was thinking about, what I was showing you is a little bit secondary. It's like calculating from the GITT experiment, you can get a diffusion coefficient from those relationships, but to generate those relationships in the first place is a separate kind of a thing. So what I was showing isn't exactly the answer to your question. So yeah, sorry, I'm not 100% sure the equation to describe that. Anyway, it always makes me try to remember the specifics of PIT and GITT. But anyway,
But hopefully this at least like helps you with your modeling.
Yeah.
Minimally.
Yeah. Look for an inverse square root of time dependence on potential. It's probably going to be something like that.
Yeah.
So
like don't model it versus an exponential or something like that.
Yeah, most probably.
Probably not that.
Okay. We're going to call it here, I guess.
Yeah, it's 3 o'clock. We went the whole 2 hours.
We did.
We got through, I think, all
There's
the questions.
one other question. We'll just save it for next week, I guess.
Okay.
It's fine. It was from last week. I was going to talk about a thing, but I'll do it next week.
Okay.
So cool.
Oh, yeah. Yeah. The time of the battery thing.
Yeah.
Yes.
Yeah. I can talk about that next week.
Yeah.
So, all right. Well, anyway, thank you, everybody. We appreciate your questions and your engagement as always, I guess. Always some interesting questions and making us think and stretching us to our absolute limits of bad electrochemistry.
Yeah.
Or good electrochemistry, however you look at it. Well, in any case, we thank everybody again, and we will see everybody next week, I suppose.
Yeah.
Have a great weekend.